Hello, welcome to the talk of the paper Uncommon Belief in Rationality, co-authored by Qi Shi and Pavel Nomov. I will first talk about rationality and belief in rationality in multi-agent settings, and introduce the proposed graph-based language, RBR graphs. Then I will use an example to illustrate how rationality and belief in rationality affects the reasoning process, and introduce the solution concept, rationalizability. Third, I will introduce the major technical results, the equivalence condition, and the minimization algorithm for RBR graphs. In the study of game theory and game model multi-agent systems, common knowledge of rationality is almost an orthodox assumption. This assumption consists of an infinite sequence of statements like every agent is rational, every agent knows that every agent is rational, every agent knows that every agent knows that every agent is rational, and so on. In epistemology, knowledge is defined as something that must be true and justifiable. However, in multi-agent settings, it is hard to say that the rationality of other agents is justifiable from the standpoint of one agent. So the assumption of common knowledge of rationality is too strong. Luckily, what affects the reasoning process in multi-agent interactions is not the knowledge of rationality, but rather the rationality of each agent and their belief about the other agent's rationality, where belief does not have to be true or justifiable. As a replacement for a common knowledge of rationality, researchers came up with the concept rationality and common belief in rationality, abbreviated as RCBR. Technically, RCBR has two meanings. One says that rationality is common, which means every agent is rational. The other says the belief in rationality is common, which consists of an infinite sequence of statements like every agent believes that every agent is rational. Every agent believes that every agent believes that every agent is rational, and so on. We found that RCBR is describable with a complete diagram, whose nodes represent the rationality of agents and the edges capture the idea of belief. For example, in a system of three agents ABC, the node labeled with A represents the statement that agent A is rational. The path ABA captures the statement that agent A believes that B believes that A is rational. Obviously, our CBR is still too strong as an assumption. First, rationality might not be uncommon. For example, when agent C is too young a child to possess rationality, or say the ability to do mathematical reasoning, then only agent A and B are rational. RCBR exists between A and B, but neither of them believes that C is rational. In this case, rationality and belief in rationality can be described with the diagram shown here. Of course, this requires an assumption that irrational agents act arbitrarily, so their beliefs about other agents' rationality are irrelevant in our analysis. Let's consider another case where belief in rationality is uncommon. For example, suppose that the young child C is a genius who is smart enough to possess rationality. She also notices the arrogance of A and B, so she believes that neither A nor B believes herself to be rational. In this case, all three agents ABC are rational. RCBR exists between AB, and the child C believes RCBR exists only between A and B. In this example, rationality and belief in rationality can be captured by this new diagram. However, if child C does not notice the arrogance of A and B, then C would believe RCBR exists among all three of them. Then rationality and belief in rationality can be captured by the diagram in this slide. Notice that in this case, child C has wrong belief about the belief of A and B, so the agents A, B in C's belief are not the real A and B. In this diagram, we use the solid nodes to represent the real agents A and B, and the dashed nodes to represent the disaster agents A and B in C's belief. In this paper, we use diagrams with solid and dashed nodes to capture any common or uncommon rationality and belief in rationality in multi-agent systems. We call these graphs RBR system graphs. This is a major contribution of the paper. In RBR graphs, nodes represent the rationality of real or disaster agents, while the label sequence of any path of at least two nodes captures a belief statement. We use RBR graphs as a graph-based language to express any RBR in multi-agent systems. It replaces, for example, formulas in stochastic logic. Next, Let's see how RBR affects agents' behavior in interactions. To answer this, the core is the question, what is rationality? In the literature, a rational agent, when faced with uncertainty, first forms a subjective probability distribution over all possibilities and then chooses a strategy that best responds to the subjective probability distribution. In this way, a strategy is called rationalizable if it best responds to some subjective probability distribution. The process of finding rationalizable strategies is called rationalization. In this paper, we simplify the definition of rationalization as the elimination of strongly dominated strategy in pure strategy space. We have a deeper discussion about this simplification in the paper. To briefly illustrate how rationalization works in games, we take a simplified guess 2/3 of the average game, for example. In this game, each agent chooses an integer in the interval 1 to 10. The one whose choice is closest to 2/3 of the average of the other agent's choices wins. So for each agent, 2/3 of the average of other agents' choices is the target to approach. Let's consider the first case where RCBR exists among agent ABC. The action space for each agent is the interval 1 to 10. So the target of each agent is in the interval 2/3 to 6 and 2/3. Then 7 is definitely closer to the target than 8, 9, and 10. So rationalizable choices are 1 to 7 for each agent. However, because of RCBR, every agent should believe that the choices of other agents are in the interval 1 to 7. Then the new target is in the interval 2/3 to 4 and 2/3. So the rationalizable choices become 1 to 5. Again, because of RCBR, every agent believes that every other agent would choose from 1 to 5. Then they do rationalization once again, and the process goes on and on and on. Finally, the only rationalizable choice is 1 for each agent. This is standard analysis in epistemic game theory. Now we consider the second case. By our assumption, the irrational agent C always arbitrarily choose from 1 to 10. A and B choose it from 1 to 7 because they are rational. Next, because A believes that B is rational but C is not. So A should believe that B would choose from 1 to 7 and C would choose from 1 to 10. So A will choose from 1 to 6. The same is true for B. A similar rationalization process goes on and then reaches a stable state where A and B choose from 1 to 5 and C choose from 1 to 10. Now we can consider the third case, where agents A and B have the same beliefs as in the previous case. So their rationalization process should be exactly the same. For C, initially she will choose from 1 to 7 because of her rationality. C believes that A and B are rational and choose from 1 to 7, so she chooses from 1 to 5. In this RBR graph, we can see that whatever agents A and B believe, agent C believes in such beliefs. So agent C would also believe that A and B would choose from 1 to 6. So her new rationalizable choices would be 1 to 4. The rationalization process goes on and on. Finally, it reaches a stable state where A and B choose from 1 to 5 and C chooses from 1 to 3. For the last case, observe that agents A and B have the same beliefs as in the second case, while agent C has the same belief as in the first case, so their rationalization process should be identical to the corresponding cases. In the above analysis, we can notice that RBR implies an iterative rationalization process until a stable state is reached. Such a stable state is a solution concept called rationalizability in the literature, but especially for RCBR. In this paper, we propose the solution concept called disaster rationalizability to capture the stable state of the iterative rationalization process in any given RBR system. This is another major contribution of this paper. Next, I will briefly introduce the technical results of the paper. We have noticed that some nodes in RBR graphs represent identical belief. For example, all three circled A-label nodes represent that agent A believes that RCBR exists between B and herself. Formally, we define two nodes to be equivalent if they have the same rationalizable choices in the disaster rationalizability of every game. We prove that two nodes are equivalent if and only if they are labeled with the same agent and the set of label sequences starting at them are the same. Informally, that is, the two nodes represent the same agent with the same belief. We also notice that some RBR graphs may represent identical RBR. For instance, the right RBR graph illustrates RBR of each agent separately, but both RBR graphs capture that RCBR exists between A and B, and C believes RCBR exists among A, B, C. Formally, we define two RBR graphs to be equivalent if they lead to the same disaster rationalizability in every game. We prove that two RBR graphs are equivalent if and only if, for each agent, solid nodes labeled with this agent either exist in neither graph or exist in both graphs and are equivalent. That is, either the agent is irrational in both graphs or is rational and has the same belief in both graphs. We also work on the minimization of RBR graphs, that is, to compute an equivalent RBR graph with the fewest nodes. Our theorem shows that the equivalence of RBR graph is, in essence, the equivalence of some sets of label sequences, the latter of which reminds us of the equivalence of regular language. This shows a similarity between the minimization of RBR graphs and the DFA. Following this intuition, we design an algorithm that minimizes any input RBR graphs whose time complexity is big O A times n squared log n, where A is the number of agents and n is the number of nodes in the input RBR graph. This is the end of the talk. Thank you very much for your attention.